Welcome to the lectures session for diploma students. In today's lecture, we are going to analyze the electrical networks by implementing a famous theorem called as Thevenin's theorem. So, Thevenin's theorem provides a method for simplifying a circuit to a standard equivalent form. This theorem can be used to simplify the analysis of complex circuits. Any bilateral network may be reduced to a simplified two terminal circuit consisting of a single voltage source VTH in series with a single resistor. So, in this Thevenin's theorem there are two important parameters upon which the whole analysis of Thevenin's theorem is focused on. One is the Thevenin's resistor, that is RTH, and the other one is the open circuit voltage VTH. Procedure: remove the load resistance RL and put an open circuit across the terminals. Number 2, find the voltage across the open circuited terminal VTH or VOC. Thirdly, find the equivalent resistance RTH as seen from open circuited terminals by replacing the voltage source by its internal resistance. Then draw the Thevenin's equivalent circuit by a voltage VTH in series with the equivalent resistance RTH. Finally, find the current through the load resistor RL by applying Ohm's law. So, this is the network to be analyzed. So, whenever you have a network like this, first of all, as a first step we need to open circuit the load resistor. So, this has to be open circuited. Step 1, open circuit the load resistor. After open circuiting this, so there are two open circuit terminals A and B. Then step 2, find open circuit voltage. So, across this terminals A and B we need to find out the voltage, which means that, so we need to find out the voltage across the resistor R2, which will be the open circuit voltage across the terminals A and B. So, VTH is the potential across the terminals A and B, which is equal to I into R2. So, the current passing through the resistor into the value of the resistor will give you the open circuit voltage. So, I is equal to E by R1 plus R2, because R1 and R2 are series. Whenever this load resistor is open, it is no more a two loop system, it becomes a single loop system. So, the current passing through R1 and R2 will give you that is the VTH is equal to total voltage divided by R1 plus R2 into R2. Third step is we need to find out Thevenin's equivalent resistance. For finding out the Thevenin's equivalent resistance, we can compare the previous diagram. Here there is a open circuit here, but the voltage remains as such. For finding out Thevenin's equivalent resistance, the open circuit remains as such, but the voltage source is being short circuited or it is replaced with its internal resistance. Here, since there is no internal resistance given, we are going to just make it short, and this is called as Thevenin's resistance or Thevenin's looking back resistance. So, we should start calculating the resistance from this end towards this short. So, whenever you calculate this, so R3, R1 and R2 are parallel. So, which is represented as R12, which is reduced to R1 into R2 divided by R1 plus R2. So, once this is made, the resistance, the circuit will become like this: R12, then this is R3, this is A, this is B. So, we have made these two resistances as a single one called R12 by applying this formula, equivalent resistance formula. Then there are two resistances in series. So, the Thevenin's looking back resistance RTH across the terminals will be RTH is equal to this R12 plus R3, because these two are in series. Then we need to arrive at Thevenin's equivalent circuit. Thevenin's equivalent circuit is nothing but it is a single loop system where you have VTH, that is the open circuit voltage, as a source, and RTH is being connected to the load resistor in series. So, whatever load resistor we have eliminated on the first step will be included into the terminals A and B along with RTH and VTH. Last step is we need to find out the load current. What is the load current here? So, IL is equal to VTH divided by RTH plus RL, because RTH and RL are in series. Now, we will work out a problem based on Thevenin's theorem. Here is a circuit given. Obtain the Thevenin's equivalent circuit at terminals P and Q of the following active network. So, already the load resistor has been removed actually across the terminals P and Q. So, the given data is supply voltage is equal to 10 volts. We need to find out the Thevenin's equivalent circuit. So, for that we need to find out Thevenin's looking back resistance or Thevenin's resistance and open circuit voltage. So, step 1, find the open circuit voltage. So, open circuit voltage is nothing but it is the voltage across the open circuited terminal, which is nothing but the voltage across the 30 ohm resistor. So, it is a single loop. What we can do is we can calculate the current passing through 30 ohms, which is equal to 10 volts divided by 40 plus 30. So, this current into the resistance will yield you the open circuit voltage. You see here VTH is the potential difference across the terminals P and Q. Potential difference across the terminals P and Q is equal to potential difference across the 30 ohm resistor. So, VTH is equal to I into 30, I is equal to 10 by 40 plus 30, 40 plus 30, yes, plus 30, and VTH is equal to 0.14 into 30, which will yield you 4.2 voltage. Step 2, you need to find out RTH. For that I have already told you, to find out RTH you need to replace all the voltage sources by its internal resistance. If internal resistance of a voltage source is not at all given, you replace that with a simple short circuit. Here I am going to make it as a simple short circuit here. Then we need to find out the Thevenin's looking back resistance starting from this. So, here 2 ohms and 40 ohms are in series. So, I can make it as a single resistor like this, which is 42, then 30 ohms, then 20 ohms here. So, this is your next step. So, P and Q. Again this is 42, this 42 and 30 are parallel. So, we need to find out R123 by simplifying further. So, 42 into 30 divided by 42 plus 30 will yield you 17.5 ohms. So, these two can be made as a single resistor, this parallel combination, that resistance value is 17.5 ohms. Again it is 20 ohms here. So, P and this is Q. Now, the equivalent resistance or Thevenin's looking back resistance is 20 and 17.5 sum, right. So, which is equal to 37.5 ohms. So, the first step is over. The second one is, sorry, the third step is we need to draw the equivalent circuit. So, this is the VTH we got, which is 4.2 volts, and this is the RTH 37.5. Suppose if you have any load resistor over here, you can straight away connect the load resistor and find out the current which is passing through the load resistor later. So, the main idea of implementing a Thevenin's theorem is, if you have n number of loops, say for example 7 or 8, you could not be able to implement mesh method or nodal method or Kirchhoff's voltage law straight away, because it is cumbersome. Instead of that, you can replace all the voltage sources by a single voltage source called as open circuit voltage and a single resistance called as Thevenin's looking back resistance which is connected in series with the load resistor to calculate the magnitude of current. So, it becomes as simple as that. The next problem is determine the current flowing through 5 ohms resistor by using Thevenin's theorem. Here we need to calculate the current passing through this. So, the first step is we need to open circuit this. We should make it open. So, first step is we have made it open and named the terminals as P and Q. Then we need to find out the open circuit voltage VTH. So, VTH is equal to the potential difference across the terminals P and Q are the potential difference across the 2 ohms resistor minus 12 volts, because in addition to that you have a you can see here. Suppose if this particular voltage source is not there, it is just the current into this resistance will yield you VTH. Since the presence of 12 volts here, so VTH will be like this. So, potential difference across 2 ohms resistor minus 12 volts. So, VTH is equal to I into 30, which will yield you 5 amperes of current, then VTH is equal to minus 2 volts. And then we need to find out RTH. For this we need to replace all the voltage sources by its respective internal resistance. If there is any current source, we need to open circuit it. Then find out RTH. So, here is a parallel combination of 2 ohms. So, 2 into 2 by 2 plus 2, which will yield you 1 ohm. So, this 1 ohm in series with 8 ohms. So, this is your P and Q terminal. So, 1 ohm, this is 8 ohm. So, RTH is equal to 1 plus 8, 9 ohms. So, then draw the equivalence, that is Thevenin's equivalent circuit. RTH is equal to 9 ohms, VTH is equal to 2 volts, RL is equal to 5 ohms. Load current is nothing but it is IL is equal to VTH by RTH plus RL, which is equal to minus 0.0143 amperes. So, the minus sign is indicative of the direction of the current. Whatever we have assumed is wrong, we should assume in the other direction. Determine the current flowing through the 6 ohms resistor by using Thevenin's theorem. Here this problem is entirely different from the previous one, for the fact that in the previous problems we do not have any internal resistance for the battery, whereas here the battery 6 volts is having an internal resistance of 0.5 ohm, and similarly the battery is having 12 volts is having an internal resistance of 0.5 ohm. So, we need to find out the current passing through the load, that is 6 ohms. First step, open circuit the load resistance and name the terminals P and Q. Step 2, find out the open circuit voltage VTH. VTH is equal to 12 volts minus potential difference across 3.5 resistor. So, this is the 12 volts minus potential difference across the 3 ohms will yield you the voltage across the P and Q terminals, or in other words we can say 6 volts plus potential difference across 2.5 resistor. So, 6 volts plus the potential difference across potential drop across 2 ohms resistor. So, potential drop across 3 ohms resistor is I into 3.5. So, I is equal to 1 ampere. So, the potential difference across the 3 ohms resistor is equal to 1 into 3.5, which will yield you 3.5 volts. So, VTH is equal to 12 minus 3.5, so 8.5 volts. So, the first parameter of the Thevenin's theorem is obtained. Then the next one is we need to find out the Thevenin's equivalent resistance. So, without disturbing these two terminals, we need to find out the equivalent resistance. How can we do that? So, we can have P and Q terminals like this. So, without altering this, you have 3 ohms, here you have 0.5 ohms connected here. Similarly, you have 2 ohms here and 0.5 here. Now, from across the terminals, if you see, the resistances 3 and 0.5 are in series, the resistances 2 and 0.5 are in series. So, I can make these two resistances as a single one, which is 3.5, then I can make these two as a single one, which is 2.5 across P and Q. So, this is equivalent to this. Now, again we can simplify this 3.5 volts, 3.5 ohms and 2.5 ohms are parallel to each other. So, 3.5 into 2.5 divided by 3.5 plus 2.5, which will yield you a resistance of 1.46 ohm. And finally, with the parameters of RTH and VTH, we can derive at Thevenin's equivalent circuit. Then load current is found out, VTH divided by RTH plus RL, which is 1.14 amperes. The current through 6 ohm resistor is equal to 1.14 amperes. Now, we will switch on to a slightly more complex problem, which has got 3 loops, or we call it as a Wheatstone bridge. This is called as Wheatstone bridge. Here we need to find out the current passing through 10 ohms resistor using Thevenin's theorem. First step is open circuit the load resistance and name the terminals A and B, and then mark the direction of currents. This is I1, this is I2, here is I1 plus I2, because I1 is coming over here, this is I2. So, by applying KCL at this node A, what happens is this is outgoing current. So, the algebraic sum of incoming currents is I1 plus I2, that should be equal to the outgoing current. So, X should be I1 plus I2. So, the same I1 plus I2 goes here, I1 plus I2, and then splits into 2 I1 and I2 again. So, this process goes on. Now, to find out the open circuit voltage, we need to find out the voltage at point A and the voltage at point B. Voltage at point A and voltage at point B. VA is equal to supply voltage minus potential difference across 1 ohm resistor, that is potential difference across 1 ohm resistor is I1 into 1, which is equal to 1.67 into 1 volts. So, similarly, VB is equal to supply voltage minus potential difference across 1 ohm resistor. Potential difference across, sorry, it is not, it is 4 ohm resistor, it seems. Yes, 4 ohm resistor, not 1 ohm. It is 4 ohm across 4 ohm resistor. So, potential difference across 4 ohm resistor is I2 into 4, I2 is equal to 1.43 amperes, and respective potential drop across 4 ohms is calculated as 5.72. Then finally, the difference between VA and VB will be the Thevenin's voltage, which is 1.67 minus 5.72, yielding minus 4.05 volts. Then the next step is to calculate Thevenin's equivalent resistance. How to calculate Thevenin's equivalent resistance? So, RTH is equal to 1 into 5 by 1 plus 5. So, these two are parallel, 1 into 5 by 1 plus 5. So, I can redraw this more clearly like this. This is A, 1 ohm, 5 ohm, here is a short, then you have 4 ohm, here you have 3 ohms. So, here is B. So, 1 into 5 by 1 plus 5 is 1 equivalent, and 4 into 3 by 4 plus 3 is another equivalent. So, both are in series. So, you will have 5 by 6, 12 by 7. So, this is the terminal A, this is the terminal B. So, finally, addition of these two will yield 2.54 ohms. So, the Thevenin's equivalent resistance is 2.54 ohms and here it is 4.05. So, already we got VTH is equal to minus 4.5. So, for that reason I have changed the terminals as minus and plus. Had it been 4.05 alone, positive 4.05, then this will be plus and this will be made minus. Then we need to find out the load current. IL is equal to VTH by RTH plus RL, which will give you value of 0.32 amperes. So, the current passing through 10 ohms resistor is 0.32 amperes. Then comes a very important theorem called as Norton's theorem. Norton's theorem is very much similar to Thevenin's theorem in the fact that we need to find out the equivalent resistance. So, 50 percentage of Thevenin's theorem analysis is same as that of the Norton's theorem, and the other part is instead of V naught we will be finding out the open circuit EMF parameter in Thevenin's theorem, whereas here we will be finding out the short circuit current. So, that is the only difference. The other parameter, that is the resistance, is same here. Norton's theorem is a method for simplifying a two terminal linear circuit to an equivalent circuit with only a current source in parallel with a resistor. This basic difference between Thevenin's theorem and Norton's theorem is that Norton's theorem results in an equivalent source in parallel with an equivalent resistance. The equivalent current source is designated as IN and the equivalent resistance is designated as Rn. To apply Norton's theorem, you must know how to find the two quantities IN and Rn. Norton's theorem states that any two terminal network can be replaced by a single current source IN in parallel with a single resistance Rn. Procedure: number 1, remove the load resistance RL and put a short circuit across the terminals. That is the first point. Now, you can compare this with Thevenin's resistance, where you can remove the load resistance and keep that resistance as open circuit. Secondly, find the short circuit current. Here also you can compare this with the Thevenin's theorem. Here you are finding out the short circuit current, there you will be finding out the open circuit voltage. Thirdly, find the equivalent resistance Rn as seen from the open circuited terminals by replacing the voltage source by its internal resistance. This is common with, third point is common with Thevenin's theorem. Fourth one is draw Norton's equivalent circuit by a current source ISC in series with the equivalent resistance RTH or Rn. Whereas here there is a difference. In Norton's equivalent, what you will be doing is you will be keeping a current source ISC parallel to the equivalent resistance or Thevenin's resistance. When you compare this with the Thevenin's theorem, there you will have open circuit voltage connected in series with the Thevenin's resistance. So, that is the only difference. And finally, find the current through RL by applying current division rule. So, this is total current. So, opposite arm resistance and then total resistance. So, here is a circuit for explanation. So, RL is the load resistor through which the magnitude of current is to be found out. First point, remove the load resistor RL and short circuit its terminals. So, when you compare this with the previous one, so now we are going to remove this RL and make it as short. So, that is what it has been done here. So, it has been short and we are going to find out the current passing through this short circuit and name it as ISC, that is the current short circuit, and name that is the mark the currents passing through the branches. Step 2, find the short circuit current or Norton's current. So, this can be found out by any method. So, you can employ Maxwell's mesh method, you can employ nodal method, or you can just apply current division rule. Since you have only one voltage source here, mere application of current division rule will yield the magnitude of current passing through the terminals A and B. So, simply we can straight away apply current division rule to find out this. So, the equivalent resistance is equal to R1 plus R2 into R3 divided by R2 plus R3. So, this is the parallel combination of R2 and R3 plus R1. So, because R1 is connected in series, current I1 is equal to E by R equivalent. So, ISC is equal to, by current division rule, total current into opposite arm resistance divided by R2 plus R3. This is exactly same as that of your Thevenin's resistance. You replace all the voltage sources. Here we found a voltage source earlier, now it has been made short to find out the Thevenin's looking back resistance. That is, we no more call it as a Thevenin's looking back resistance or Thevenin's resistance. In Norton's theorem, the terminology is entirely different. We call it as a equivalent resistance. So, from here, from A and B, without disturbing the terminals A and B, we will be calculating this. So, R1 and R2 are parallel, so which is given by R12, and then Rn is equal to R12 plus R3, because R3 is connected in series. Then this is the Norton's equivalent. So, this is the current source, the resistance, that is the equivalent resistance, is connected in series, parallel with the current source, and then the earlier eliminated load resistor is again connected here. So, you can see the difference in Thevenin's theorem. You can compare, you will have a voltage source in series with RTH, in series with RL, whereas here all are in parallel, current source, Rn and load resistor. Finally, load resistor can be obtained by applying current division rule. So, we can have a quick recap of whatever we have studied today. So, in today's class we have done problems on Thevenin's theorem, and 2 loop system, 3 loop system we have done, and also we have done some analysis on Norton's theorem also. We have learnt the difference between Thevenin's theorem and the application of Norton's theorem. We are yet to do some problems on Norton's theorem in the coming classes. Thank you.